A regular expression, also referred to by its abbreviation as regex, provides a powerful way to process text data. Regex is often an indispensable tool for applications that deal with parsing strings. Common use cases for regex include validating text input, performing complex searches for matches of patterns within strings, and for removing or replacing portions of a string. A regular expression pattern is made up of a sequence of characters. Each character can represent either a literal character or a meta character which has a special meaning within the pattern description. The regex syntax can be quite intimidating at first glance, and advanced patterns can look more like a cat has just walked across your keyboard. With time though, the syntax does become easier to interpret, and many tools exist to assist with producing and testing more complex expressions. The syntax of regular expression patterns can be applied in most other programming languages, and provides a consistent way to handle text manipulation. Languages may use different regex engines, the central component responsible for processing them, and some features may vary. .NET uses a backtracking regular expression engine that incorporates a traditional non-deterministic finite automaton NFA engine, such as that used by Perl, Python, and Emacs. Backtracking support allows the engine to save state as it attempts to match text, returning to previous state to attempt additional matches when necessary. The .NET regex engine offers greater control over string matching, but a potential cost of this flexibility is that matches can run more slowly if the pattern is complex and requires lots of backtracking. In .NET, we represent the regular expression pattern itself as simply another string. This example pattern will match any string that begins with the uppercase Latin letter A. It will also match the remaining characters that follow. When using regular expressions in .NET, we can check whether an input string matches a pattern, but we can also call methods which return the substring that matched the pattern. At the start of the pattern, the caret metacharacter signals that we require the match to begin immediately at the start of the string and not just randomly somewhere within the source string. The literal uppercase character A must appear immediately at the start of our string. The period metacharacter will then match any character except for line terminators. We want to match any number of trailing characters, and that can be achieved by including the star metacharacter. The star metacharacter signals that we want the previous token, the period, to match 0 or more times. It creates something we call a greedy match, meaning that we want to match the longest possible sequence of characters that follow the uppercase letter A. With the pattern defined, we can use it with either an instance of the regex class or through one of the available static methods on the regex type. Using these static methods is generally recommended, as caching can be applied to mitigate some of the performance impacts of using regex in our applications. As an example, we can call the regex isMatch method with two arguments. The first argument is the input string that we want to try and match. The second is the regular expression pattern to use for matching. isMatch returns a Boolean result which will be true if the pattern was matched within the input string. In this example, the value of isMatch will be true because the input string begins with the letter A and therefore matches our pattern. Here are the results of using this same pattern to match other input strings. This match fails because the first letter is a lowercase letter A, and we expect it to be uppercase. The second string here matches because it starts with an uppercase letter A. The whole string will match even though there's another uppercase letter A later in the string. This string does not match because it starts with an uppercase letter T. And while there is an uppercase letter A later in the string, our pattern specifically required to match at the beginning of the string. A single uppercase letter A also matches because we use the star token to require 0 or more characters after the first letter. If we tweak our regex pattern slightly, we can change the behavior. Instead of a star, we'll finish it with a plus. The plus meta character signals that the previous token should occur one or more times. If we compare the results of both patterns, the only difference is in the last match. We don't match on a sole uppercase letter A with the new pattern because we expect one or more characters to follow it. If we only need to test for the presence of an uppercase letter A at the start of a string that's followed by at least one character, then we can simplify this pattern and omit the final plus meta character. This can improve the performance a little because we're no longer performing a greedy match of all remaining characters that follow the initial letter. If we only need to match and identify strings that start with an uppercase letter A, this would be sufficient. However, this second column shows the string we would match using another of the regex methods. We'll learn more about this method later in the course. Match uses the provided pattern to return the portion of the string which matched the pattern. Because our pattern is not greedy, only the letter A and the subsequent character are included in the matched value. Regular expressions are a really deep topic, and this course cannot cover every detail of using them. We will learn to apply regex in practice to solve real-world problems such as extracting, editing, replacing, and deleting text substrings. There are resources available to assist with further learning on this topic. The Microsoft documentation includes a quick reference which provides a lot of detail into the various expressions. For a deeper understanding, you can also check out Juliet's course, Regular Expression Fundamentals, here at Pluralsight.